Hi, everyone. I just wanted to give you guys kind of an introduction to what we're going to be talking about in chapter three. Um, we've been talking a lot about related rates and finding derivatives and using rules to find derivatives, but one of the most useful applications that we're going to talk about in calculus are optimization problems. And these are kind of like the most real world kind of problems that you'll really encounter in this chapter, which is basically finding out optimal ways to do things. Like, for example, a company that makes canned food might want to know the shape of the can that will minimize the manufacturing costs, or they might want to know like the minimum amount of material that it's going to take to make something. So, in order to do problems like these, we need to be able to find maximum and minimum values. So, that's what we're going to look at first today with some graphs. And some of this stuff might be familiar. That's why I wanted to kind of give it to you guys in a video because um, it's probably pretty intuitive. But I want to talk about just some definitions first. So we can say that a function has an absolute maximum. Sometimes you'll see that written as a global maximum. That's why I put that there in parentheses at some value c if f of c is greater than or equal to f of x for all x in the domain D. So what is this saying? This basically says f of c is really talking about the y value at an x value of c. And this is talking about the y value, or I should say all the y values in the function. So basically, we have an absolute maximum if the y value at this x value is greater than any y value or greater than or equal to any y value in the entire function. We can kind of say the same thing about absolute minimums. We can say a function has an absolute minimum or a global minimum if our f of c value or the y value at x is equal to c is actually going to be less than or equal to f of x or the y values in the function for all x in the domain D. So sometimes you'll see maximum and minimum values referred to as extreme values or extrema. These all just mean the same thing: maximum, extreme values, minimum values, extrema, all the same thing. So if we look at a graph, and this is just kind of an arbitrary graph, we're going to identify some key points here. So we're going to identify the minimums and the maximums, and there can definitely be more than one on a graph. We have things that are called local minimums, and we have things that are called local maximums, and we have things that are called absolute minimums and absolute maximums. So the absolutes are basically like the really, really, really low point on the graph or the really, really, really high point on the graph. So if we look on this graph, we would probably say that this f of a value, since it's lower than all of the other points on this graph, this is our absolute minimum. And then this point here at x is equal to D would be our absolute maximum because it's higher than any other point on the graph. And then we're left with all these kind of other places where we kind of have like turning points a little bit. And these points also have a meaning in terms of the graph. These are actually called local maximums and minimums. So this here, it's still a maximum, but it's not the absolute because it's not the highest, but we would call this a local maximum. And then this, even though it is a cusp, this is actually still considered to be a local minimum. Again, it's a local because it's not the lowest point on the graph. And then we would say that this point at x equal to e is also a local minimum. So we can say that a function has a local maximum at c if, again, f of c is greater than f of x for all x in an open interval near c. And then a function has a local minimum at c if f of c is less than or equal to f of x, again, for all x in an open interval near C. And what does this mean? That basically means that local extrema cannot occur at endpoints of the domain. So absolutes can definitely occur at the endpoints, but we cannot say that this would be like a local anything or this would be a local anything, because what needs to happen is when we're looking for local minimums and maximums, there's got to be something around the point to compare it to. So there's got to be a left side of the graph and a right side of the graph. Over here, this point only has a left side of the graph and it doesn't have anything to compare it to on the right side of the graph. So I'm going to make a little note here that says, in order to be a local max or min, there has to be values on both sides to compare. So basically, what that's saying is that only absolute extrema or only absolute maxes or mins can occur at endpoints. So local minimums and maximums cannot occur at endpoints, only absolute can. And this is kind of a good visual representation of what that's talking about. So this is going to be definitely some sort of local point because I've got values on both sides to compare it to. This is going to be some local point. This is going to be some local point. This would not be considered a local anything. This would not be considered a local anything. It can be an absolute, but it cannot be a local. So I just want to go through a couple of examples of identifying what these maximum and minimum values are looking at a graph. So we're going to talk about the domain of this function. So the x values that we are covering for this function would be from 0 to 3 pi over 2, inclusive, because these are both filled in points. My absolute maximum value would be this highest point up here. I can make it an absolute because it's on an endpoint. So the way that we would write that, we would generally write that as a point, like 0, 1. But in calculus, the way that we would write that would be f of 0 is equal to 1. So it's telling us that at the x value of 0, our y value is 1. We also have an absolute minimum value down here. That's our lowest point on our graph. And we would say that that would be at the point pi negative 1. But again, with my notation, I'm going to write this as f of pi is equal to negative 1. A local maximum value. I actually don't have any local maximums on this graph. I do have an absolute maximum, but I don't have anything going on the inside here that's going to indicate that I have any sort of maximum besides the one that's on the endpoint. So sometimes you might not have these values. So I'm going to say none, and I'm going to look for local minimum values. So this point here, even though this was our absolute minimum, we also can call that the local minimum because, again, it's local because there's things on each side to compare it to, or there's a piece of graph on either side. So again, I'm going to write that as f of pi is equal to negative 1. So on this graph, our domain, if we look to see, we've got a vertical asymptote here at negative 1. We're going to say our domain is from negative 1 to 4. I'm not going to include negative 1 because it's not included, but I am going to include positive 4 because that is a solid dot here. And if we're looking for maximum values, you'll notice that this graph continues to increase as it does get close to that asymptote. So that actually means that there is going to be no absolute maximum because the graph is going to continue to increase infinitely. We do have an absolute minimum though, because we can see that this point down here on our graph is our lowest point. So we would write that as f of 4 is equal to 1. We also have no local maximum value. Again, if we don't have anything that's kind of wavy in between here, and we know that our graph is infinitely increasing, there's not going to be any locals. And for this one, we do have an absolute minimum, but it can't be a local because it is an endpoint. So the local minimum, we actually will say that there is none here either. All right, and we'll look at one more. So C, our domain here, is actually negative infinity to positive infinity because our graph is going to continue to kind of go outwards as the domain gets really negative or gets really positive. Again, similar to the last graph, you'll notice that our graph is going to continue to increase. So we are not going to have any absolute maximum values. There's not going to be a highest point anywhere on this graph. I do have an absolute minimum point here. This is definitely my lowest point on my graph. So that's my absolute minimum. So that looks like it's at the X value of -3. And the Y value would also be -3. I do have a local maximum because I see that I kind of have a high point here. It's not the absolute because it's not the highest point on the graph, but it's definitely local because it's kind of in between. So my local maximum looks like it's at like f of 0. The Y value is a little bit higher than 1. So I don't know, 1.25 or something like that. And then I actually have 2 local minimums here. So again, I can have more than one local minimum or local maximum. And because I do have an absolute minimum here, it can also be a local. So I actually have 2 points here. So I would say my local minimum would be f of 2.25 is equal to, I don't know, close to -1. So maybe like -0.75. And then I do have this other point here, which we already said was f of -3 is equal to -3. All right. And then I want to talk a little bit about just kind of sketching graphs. So you might be given some information and asked to sketch a graph of a potential function with given properties. So let's do this one. So I have a domain from 0 to 8. So I'll set myself up kind of a little coordinate plane here. Just make myself some tick marks. Make sure I get up to 8. I have an absolute maximum at 0. This is an X value, so this is saying X is equal to 0. An absolute minimum at X is equal to 3, and a local minimum at X is equal to 7. So I don't know, I'll kind of make myself a really high point here at X is equal to 0. I know that I want an absolute minimum at X is equal to 3. So I don't know, it doesn't even really matter where you put that. If you want to put it underneath your axis, you definitely can. If you want to put it above and just make everything else above it, that's fine too. And then we have a local minimum at 7. And then I want to end my graph at X is equal to 8. So it might look something like this. So reaching my absolute minimum down here, maybe curving up a little bit, going back down, and then curving up. And I just want to make sure that I'm hitting all my points here. So my domain is from 0 to 8. This is definitely the highest point on my graph, so absolute maximum. This is definitely the lowest point on my graph, so absolute minimum, and local minimum at 7. So this is kind of a little bit of a lower point here, but it's obviously not going to be the lowest point on the graph. And then another example, we want to do a local minimum at 4 and is continuous but not differentiable at 4. So continuous and not differentiable, I would probably say that there might be like a cusp or a corner here. So again, I'll just kind of sketch myself out a little coordinate plane here. So I have a local minimum at 4 and is continuous but not differentiable at 4. So maybe something that looks like this. So it's not giving me any specific domain restriction, so I'm just going to make it so that it kind of is continuous forever. It is continuous at X is equal to 4. This is a local minimum here, and then I also made myself another minimum. You can do that or not. It's up to you. So I'm going to have you guys try some problems from the book from homework, and let me know if you have any questions.